So last time we proved that all of P-space has interactive proofs. Okay. What was the strategy for the proof like? There were, I guess, three steps. First, how do we start? Yeah.
Arithmetization.
Of
The Boolean formula.
Right, so we picked that problem because it's complete, right? So we want to sort of put an entire class inside the IP. So we identify a convenient complete problem. In that case, it was quantified Boolean formulas. Okay, and fortunately, it was about Boolean formulas. We already knew more or less how to handle Boolean formulas by way of arithmetization. We had to figure out a few new things. For example, how to arithmetize quantifiers. But in the end, it kind of worked out. Okay, or at least we think we did. You know, it was a rather dense lecture. So far, we've seen two different types of protocols, right? So we've seen how we can arithmetize things and get rather powerful results with a large number of rounds and only public coins. Okay, but in the very first lecture, we saw a very simple protocol for graph non-isomorphism, right? We saw that. So in the first lecture, we saw that graph non-isomorphism is contained in, we can call it IP2. Okay, so it has a two-round interactive proof. By the way, a brief comment about terminology. In the literature, you will find the notion of messages or rounds to be, most of the time used interchangeably. That's rather confusing because sometimes you could think of a round as two messages, like back and forth. So yeah, whatever. I'll try to be precise. To really here we're counting the messages. But it was, anyways, it was back and forth, and we were using a secret bit, right? So in that proof, it was important the prover doesn't know the secret bit B that the verifier has flipped. Okay, so in the second and third lecture, we saw how a variety of things like coin P, P to the share P, and eventually P space have interactive proofs with a small number of rounds. And this raises the question of what is the power of private coins versus public coins. Okay, so we'll define what public coins means in a moment. But intuitively, it seems like, look, to the extent that private coins can bring any power, it cannot be in sort of which languages you decide, because we got all of P space, which is everything we can hope for, with public coins. Okay, so that's not something that private coins can bring us. But maybe this gap in round complexity here may lead you to believe that maybe if we're willing to use private coins, maybe we could save on round complexity. Okay, maybe we could prove many languages with fewer rounds. Okay, it sounds it's a very reasonable conjecture. And what we'll see today is that that's actually not the case. Okay, there is basically no difference in power between private coins and public coins. Okay, so as far as round complexity is concerned, there is no difference. Okay, no difference in power. And this should look very surprising. In particular, you should start thinking about, if there is really no difference in power, how could we have an interactive proof for GNI that has maybe two rounds and public coins? It seems surprising. Okay. Anyways, but before I get too far ahead, let's just try to define a bit more carefully what we mean by public coins. We haven't done that so far. What we've sort of seen are protocols that are public coin, but how do we define that? Oh, it's not difficult, but since we're going to be working with it, let's at least be precise. So we're going to say that a verifier V is public coin if its actions consists only of, so one, it can just sample some randomness. And send it to the prover. And two, it could just say, well, I'm done. So it will just terminate the interaction. And accept or reject. Okay? So it's a very simple type of verifier, kind of rather stupid. Okay? The only sort of interesting logic is at the very end. But along the way, it's just not really doing anything, okay? By the way, in the sum check protocol that we analyzed, we had these checks along the way, right? Without loss of generality, you can push them all to the end. So, because if the prover did something that warrants immediate rejection, if you reject right away, then he learns that, right? But you can just keep it to yourself and reject at the end. So it really is the case in a public coin protocol, or rather for a public coin verifier. During interaction, the verifier is doing nothing. Okay, it's just sampling randomness and sending it, sampling randomness and sending it. And at the very end, after he has done all these things, there is a transcript of things that have happened. Okay, and it just decides either to accept or to reject. Okay, so all the logic is encoded in this sort of second step. Okay. I guess I should say sample some fresh randomness, fresh and uniform. So just flip, some number of coins and send over the results. Okay, so it's a very basic type of verifier. Okay, in particular, notice that the prover has at any moment in time full access to the verifier's randomness, and we can define a corresponding class. It's called either AM, so let me just define it, AMK or MAK are the languages decidable via public coin interactive proofs in K rounds where the verifier or prover moves first. Wait, so just some context. So why are we calling this AM and MA as opposed to like IP? Well, first it's the IP, we don't put restrictions on public coins, and for historical reasons, the notion of public coin protocols was actually independently formulated to the notion of interactive proofs in another paper, which is linked on the website. And the person who introduced it, Laszlo Babai, sort of had this sort of mental image of a prover and a verifier as being the sort of wizard Merlin and the the King Arthur, okay? So this is called Arthur Merlin, okay? Where Arthur is bounded in power and Merlin is the wizard that has unbounded power, okay? Now, AM denotes the class of public coin protocols where Arthur moves first, so it's the verifier, so that's why you put A first, okay? And MA is when the prover moves first. Now, the difference of who moves first only makes sense when you are looking at low round complexity classes, because if you look at many rounds, then you can always pad either direction, right? You can always put a dummy message in front. But so for historical reasons, we don't really use we don't use IP to denote these public coin protocols. We use AM and MA. Okay, so asking about the question about the power of private coins versus public coins, now we can essentially rephrase it as a question of AMK or MAK versus IPK, right? So as I go up in round complexity, how do these two complexity classes compare with one another, right? Does it make sense? Now, let there's one inclusion that is trivial. Let's just say it. What's the trivial inclusion? Yeah. Right, so because we are only restricting the power of the verifier, we can, at best decide no more languages. So the less trivial part, in fact, it's a theorem, is it's a beautiful theorem and surprising theorem by Goldwasser and Zipser. I think in 87. That says that for every k, IP k is contained in AM k plus 2. Okay, so there's a constant, okay, plus 2. So you can, you can start with any interactive proof, possibly using private coins in extremely smart ways, and there's a way to turn the entire protocol into a public coin protocol, where everything is public coin, okay, and you have 2 extra rounds. Okay. Okay, this theorem, to prove it in its full generality, is rather messy. It's not something that it's good to do in lecture. But the core idea for the theorem is clean. And we can apply it specifically to GNI. Okay, in fact, for GNI, we'll be able to prove like we don't even have to pay for the +2 over there. So today, we'll prove that GNI is contained in AM k for some constant k. And if I don't mess up, I think it should be just k equals 2. But let's see later. Okay? So that's what we're actually going to prove. We're going to construct a public coin protocol for graph non-isomorphism. Okay? And this sort of special case sort of has inside it most of the intuition that goes towards proving all the theorem. I'll link the paper from the website if you want to look at how does the whole proof go. Okay? Questions so far? Okay. The idea for the theorem is really not, I mean, I think it was like a leap to come up with where to start. I'm not sure how, I mean, I know how the theorem goes, so we'll prove it in a moment. But the intuition for where to start is rather, I don't think it's obvious. So let's just jump into it. So obviously, you need to think about GNI in some sort of very different way than we have so far. Otherwise, we can keep getting stuck by this notion of private coins. So the idea is to kind of look at GNI in a sort of very quantitative way. So quantitative what? Okay, so the key quantity in question is a set. Is the set of graphs that are isomorphic to either G0 or G1. Okay? So let's define a set of graphs, H. These can be isomorphic to either G0 or G1. Notice that when G0 and G1 are not isomorphic, it means that this may not be isomorphic to both. Some H might not be isomorphic to both. Okay? Now, there are some observations that we can make about this set. The first thing is that we can certify, or rather the prover can certify, that some H is in the set S. How? So suppose that the prover wants to convince the verifier that a particular graph H is in the set S. How could it do that? Yeah.
Show an isomorphism.
Yeah, by showing isomorphism. By showing iso to G0 or G1. Okay, if the two graphs are isomorphic, it doesn't matter which one. If they're not isomorphic, well, to one of them. Okay? So membership, let's put it like this. Membership in the set S has small certificates. Okay? Okay. Now, the crucial observation is that if G0 is isomorphic to G1, then what is the size of the set S? Yeah, n factorial. Now, kind of the reason why I said I wasn't so certain is that it's not quite n factorial. What you can have in a graph is you can have a so-called automorphism group, which means that if you kind of apply, there are certain non-trivial permutations that are trivial transformations on the graph. Okay? So really, you will get n factorial sort of divided by the size of your automorphism group. That's just a detail. So for the purpose of the lecture, we're going to assume that the automorphism group for the graphs in question is trivial, is identity. Okay? So we're going to assume, so I'll just say size of S equals n factorial, and we're going to assume that automorphism group of G0 and G1 is the identity. Okay? If it's not, what you consider is an extended set where you consider pairs, which are H and the specific automorphism, the specific member in the automorphism group. Okay? And then you recover again n factorial. Okay? But for now, let's just assume that there are no elements, no non-trivial elements in the automorphism group. If G0 is not isomorphic to G1, what is the size of S? Is it n factorial squared? No, right? It's what? 2n, right? So, and then we need to be careful about sort of 2 of n factorial, right? Or 2 times n factorial, right? So, or n factorial plus n factorial, right? Notice the size is different. So, okay, that seems like a bit of a very silly observation. But the point is that the strategy to construct a public keying protocol is going to be precisely based on that. The prover will try to show to the verifier by a public keying protocol that this set is large. Okay, so it's kind of at least size 2n factorial as opposed to n factorial. Okay? Let me just write it here. It suffices for the prover to convince the verifier that S has size 2n factorial rather than n factorial, right? So in the way that this, in terms of tools, actually we will not be using anything sort of deeply algebraic. We'll be using mostly combinatorial notions of the main tool is going to be pairwise independent hashing. Okay? And by leveraging pairwise independent hashing, we'll develop a so-called approximate counting protocol that will let the verifier check approximately the size of S within a factor of 2. That's kind of good enough. Okay? Since we haven't seen pairwise independent hashing, let's just briefly recall what it is. Okay? So let's talk about it. So let H and K be a family of functions that map n bits to k bits. Okay? And we say that H and K is pairwise independent. If the following condition holds, you pick any two distinct inputs to the functions. So you can take x and x prime, and they're distinct. And you pick any two candidate images, and you ask that the probability, or you require the probability over what? So in this case, the inputs and outputs are all fixed, okay? And we're going to take a probability over a random function from the family. So you sample h from h and k, all right? You have sampled now a hash function, and now you ask, what's the probability that it is both the case that h of x equals y and h of x prime equals y prime? And you want this probability to be as if h had been completely random, okay? So it's 1 over 2 to the 2k. Okay? So again, imagine that h, the way that h operates is that on every input it outputs a random string consistently. Okay? What's the chance that for two fixed x and y and a x prime, y prime, where x prime is different than x, both of these statements hold? This one on its own will have probability 1 over 2 to the k, and this one on its own will have probability 1 over 2 to the k. And these are actually independent because x and x prime are distinct. So that's what would happen for a random function. A pairwise independent hash family is one where this specific event holds, okay? And maybe not all other properties of random functions, okay? Another way to think about it is that you can think about the joint distribution of h of x and h of x prime for h that is drawn from the family. If you look at this joint distribution as random variables, this is the same as the uniform distribution over the product space 0, 1 to the k and 0, 1 to the k. Okay? That's why we're calling this pairwise independent, because it looks like, two random outputs. If you look at 3 outputs, it doesn't mean that they are just if you look at 2. Okay? Okay, so this is the notion of pairwise independent hashing. It may look sort of similar to notions you might have seen before. For example, this is strongly reminiscent of what notion for hashing? Universal hashing, right? So you probably have seen universal hashing before. It's a slightly weaker condition, okay? This is also sometimes known as strongly universal hash functions, okay? Anyway, it doesn't matter. We're not talking about universal hash functions today. Let's just give so that we sort of feel that these things exist and make sense. Let's just look at a simple example, okay? By the way, it's important to know that these things exist efficiently because the verifier is going to have to deal with them, right? So we need to make sure that we have efficient constructions of these hash functions. So let's first look at an example where we have the size of the input and the size of the output consist of the same number of bits, okay? So we're going to first look at this as such a family, and then we're going to see how to derive something where k is smaller than n. Okay, first we're going to define this family to be all functions that are indexed by a and b, and they just apply the linear transformation on x plus b. And what are a and b? A and b are elements in the finite field of size 2 to the n. Okay? Remember that there is a finite field for every prime power. Here we're looking at the finite field of size 2 to the n. Okay? So let's see why does this work? Well, let's see. If h of x equals y and h of x prime equals y prime, then it means that we have simultaneously two equations that hold. Ax plus b equals y, and ax prime plus b equals y prime. Right? These are two equations that hold simultaneously. Right? So this event is is this event for this family. Okay? Now, this is also equivalent to A being y minus y prime divided by x minus x prime, and B being whatever is implied, y minus ax. Right? Notice that the denominator is not 0 because x and x prime are distinct. Okay? But this is the same as a not this is the same, but this implies that the probability over A and B that A equals y minus y prime and x minus x prime and B equals y minus ax is what? Right, so let's think about now what's happening. X prime, y, and y prime have all been fixed. Okay? Here's one thing that they induce, and then here are some other coefficients they induce. Now we pick A and B at random from the finite field of size 2 to the n. And we ask, what's the probability that A equals this thing and B equals this other thing? Yeah?
1 over f squared, or order of f squared?
Yeah, so 1 over f squared, so 1 over 2 to the 2n. Right? Because these are just, we're picking two elements at random independently, and we're asking what's the probability they equal these two particular elements. Okay? Okay? Fine. So notice also that linear functions are easy to compute, right? It requires one field multiplication and one field addition. Okay? Now, what we want, though, is not a hash function family where the number of inputs coming in and number of inputs coming out is the same. Okay? What we really want is well, we don't know yet what we want, but I'm telling you what we want. What we want is h and k with k having the possibility that k is less than n. Okay? So are there any suggestions of how we can basically derive such a family from the one that we just looked at? Yeah? Sorry? Yeah, or a suffix. We just do some truncation, okay? Because on this finite field, the uniform distribution over elements induces a uniform distribution over the coordinates. This is due to the kind of vector space structure of the way that finite fields work, right? Because I can think of this guy also as an n-dimensional vector space over the base field, right? And the way that sort of each of the coordinates work inside here is uniform, right? Sort of kind of I project on an equal coordinate, I get something uniform. So it's enough for me to truncate. A concrete way, algebraic way to express that is to pick the suffix. And so I can write h and k is the family that you obtain by considering h, a, b, x. And I take ax plus b mod 2 to the k. Okay? So I just look at the last k bits. Okay? Okay, so this is an example of a family. It's very simple, right? So easy to compute. Are we all convinced this is a pairwise independent hash function family? And by the way, we have no restrictions on k. We pick k to be whatever it is, between 1 and n, right? Okay. All right. That's the definition of pairwise independent hashing. That's an example of such a thing. What do we do with them? So here's the idea that Goldwasser and Zipser introduced, is that of a set lower bound protocol. Okay? So now we're going to take a step back. We're going to forget for a moment that we came from this particular problem. And we're going to think about a class of abstract problems where the prover wants to convince the verifier that a certain set has large size. Okay? So let's give a name to that set. Let S be a set for which we can efficiently certify things that look like X is in S. Okay, the S that we considered is of such a form. Now, let capital K be a number known to both parties. And let little k be basically like a power of 2 of things close to k. So specifically for this time around, I will want 2 little k minus 2, strictly less than big K, which is at most 2 to the little k minus 1. Okay? Now what we want is a protocol with completeness and soundness that work as follows. So in the completeness, we want if S is at least the target size capital K, okay, so this is the good case where S is large, where large is determined by the parameter capital K, then what we want is that the probability of accept being what? We want 1, okay, but today we won't achieve that. So instead, we'll say it will be large. In this case, it will be 3/4 of capital K divided by 2 to the k. Okay? And if S instead is small, namely less than capital K over 2, then we want the probability of accept to be small. And in this case, it will be at most a half times this same quantity. Okay? Now, when you see these two things, the first thing they should try to think about is the gap between the two cases. That's what really matters. Okay? So what's the gap? Like, just to make sure that we can see the gap as a polynomial time machine. What is the gap between this probability and this probability? Wait, what's 3/4 minus a half? A quarter, okay. So the gap is a quarter times capital K divided by 2 to the k. And this is at least what? By my choice of parameters. 1/16, right? So in other words, it's important to feel that in this setting of parameters, there's a constant probability gap between the two cases. So for example, it suffices to repeat this test in parallel a constant number of times to experience it, say, with half probability. And you can repeat it even more times if you want to experience it with even higher probability. Okay? So we haven't really seen these things, by the way, in this class. If you repeat things, what happens, okay? But I think these are sort of simple probabilistic arguments, right? So if you have these two events, and one of them happens with a certain probability and with another probability, and these things are bounded apart from each other, then by Chernoff bounds, sort of, the more you repeat this, the more these two events will kind of, the gap will kind of grow exponentially, right? So this means that this is good enough gap to fill it as a polynomial time machine. And okay, that's enough setup. What does the protocol actually do? Okay, so these are the guarantees that we're going to give. The protocol, I'll put it here instead of the example. Goes as follows. So you have the prover. That's the verifier. So the verifier will sample a hash function from the family HMK. Okay, which M? M is the number of bits in elements in S. Okay, in which k? Well, k is the little k is the one that was chosen depending on capital K, the target size. Then it also picks a random element in the image of the function, and then it sends them to the prover. Okay, so I think at this point, we should be able to guess the rest of the protocol. There's only one more message. And what do you think the verifier is trying to challenge the prover with this message? So imagine that S is really, really, really huge. For example, it is 0, 1 to the n, like everything. Okay? What becomes easy for the prover right now? Yeah?
Try to find another, like what h of, like x such that h of x equals y?
Yeah, to find a pre-image. So right now, the intuition here is that the verifier is trying to ask the prover, okay, you think S is so big, let me give you a random sort of inversion challenge. Okay, please find a pre-image of y. Okay, if S really is so big, then you ought to be able to have a high probability of being able to find a pre-image to y. Conversely, if y is very tiny, let's say really extreme, S has one element. Okay, what are the chances that the verifier picked y so that y under H has a pre-image in S? Very small, right? Because there is only one option, right? And what we're actually going to prove is that somehow the completeness and soundness are precisely related to the size. Okay? So let me just complete the protocol. What the prover has to do, it has to find x in S such that h of x equals y. Okay? And then it will send x. Now, of course, it cannot send x alone. It has to do something more, right? Because if it just sends x, it can just invert h and y, right? What else should it do? Yeah.
Send the certificate that x is an S.
Yeah. So it should sort of, so I guess, compute a certificate pi sub x that x is an S, and it will send this pi sub x over. Okay? Now, what should the verifier do with this information? First, it should check that indeed h of x is a valid pre-image of y, right? And second, it should make sure that x really is in S. Okay, it will run whatever test it has to run. Okay? Okay, so this is the protocol. Let's make sure that we understand the intuition. H is picked at random. Y is also picked at random. Okay? Notice that the prover is able to convince the verifier if and only if there is an x in the pre-image of y. Okay? So as x grows, as the size of S grows, there are more and more candidate pre-images. As S shrinks, there are less and less candidate pre-images. Okay, so intuitively, the maximum winning probability of the prover ought to be related to the size of S. Okay, this is intuitively. Now we also need to prove that by only leveraging the pairwise independent property. Okay. Does that make sense? Oh, let's start with the easy part, which is the completeness. Okay. So where do I want to do this? I kind of stuck myself here. Okay, I will move pairwise independence here, and I will use this board. Okay, so Okay, so I moved Pairwise Independence there, and I freed up this board. Okay, so which part should we do first? Oh, I don't know. Let's ask you. So which one do you think is easier, completeness or soundness? Really? I think this time soundness is easier. Huh? Yeah. Fair point. Okay, so let's do soundness first, okay? So the main thing that we want to try to prove is, let's maybe first look at this probability. The probability that over h and y, that there exists x in S such that h of x equals y, we want to derive an upper bound that has to do with the size of S. So what should we say? This is at most what? So I want to say that this event, by the way, this is the event that there exists a winning strategy for the prover, right? The probability that over the verifier's message there exists an existing winning strategy for the prover is at most what? Let's try to write it in terms of the size of S.
Size of S divided by 2 the length of
Yeah.
y.
So here we're just doing a simple union bound, right? So this probability is at most the sum. I'll just write it once because we'll be using union bounds left and right in this class. But it's at most the probability that you sum over all possible x's, right? And the probability that over h and y, that specific x is a preimage of y, okay? And what is this probability? 1 over 2 to the k. Why? Because we're kind of tracing out this event, right? So we know that this is the case, okay? But if we're willing to if we're interested in just one of these two things, we have to sum over all possibilities, right? And this one becomes 1 over 2 to the k, okay? So it's a consequence of pairwise independence. It also makes sense, right? Because remember, pairwise independence was saying that two outputs of h as a joint distribution, they act like a random the output of a random function, and stands to reason that if you look at one of them, that's certainly still the case. That it looks like the output of a random function. We're kind of tracing out the other event here. Okay, so this is the sum for x is in S, 1 over 2 to the k, and overall this is size of S over 2 to the k. Okay, so upper bounding this probability. So we'll tie this to completeness and soundness in a moment. Let's see if we can lower bound this probability. So again, I'm going to look at the probability that there is a winning strategy, and now I want to lower bound it in terms of S. Okay, lower bounding has more to do with the completeness, right? Because we want to say that if S is largish, then we want this probability to be also largish, right? Otherwise, how could the honest prover win, right? So this is the less trivial one. So the union bound is the first in a sequence of probabilistic inequalities. What's the next one in that sequence?
Inclusion, exclusion.
Inclusion, exclusion, right? So it's just this sort of Venn diagram type statements about probabilities, right? This is the next one, right? So you do inclusion, exclusion. So let's, it's I guess easier to do it in terms of events. So that at least the sum, let's try again. The sum over x in S, the probability over h and y that, so So actually, I want to make this something a bit simpler to be easier. So I'm going to take y out of the probability. Okay, so we're going to prove an even stronger lower bound. Okay. Clearly, if it holds for every y, it will also hold for a random y. Okay. So at least the sum that we have the probability that h of x equals y over a random h alone minus, and now this is where inclusion and exclusion comes, the half the probability that if I look at x and x prime, I have that it is both the case that h of x equals y and h of x prime equals y. Okay, it's probability over h. So this is just inclusion and exclusion, right? So I have this family of events, ex. Here I'm looking at least the sum of these events minus half the sum, the probability of the intersection of the events. Okay, kind of e of x and e of x prime. Okay. So what are these events? So the first one is easy, right? We just computed it. So this is sum over x in S of 1 over 2 to the k minus a half sum over all distinct x and x prime pairs. And what is this event? What is the probability of this event? 1 over 2 to the 2k. Why? Because we have pairwise independence, and x and x prime are distinct. So overall, we get this is s over 2 to the k minus a half times what? Yeah, and I think if I'm just gonna peek s squared, and if I peek s squared, it can only make things worse, right? Right? So it's okay if I put an inequality here. I'm gonna put s squared. Okay? And this is s over 2 to the k times 1 minus s over 2 to the k 2 to the k plus 1. Okay? Do you agree? There's a 2k here. Yeah. Do you agree? All right. So what is this? I can simplify this, right? At least I think I can. Oh, I forgot an assumption. So this is at least something, but I forgot to assume something. I also want to assume that the size of S is at most. I want here, what do I need here? Because I want to lower bound that, and I don't want S to be like, too big. Oh no, I assumed it here, right? Or, oh wait, no, I need to connect those things to these cases. So let's just complete, that's where I finish here, and I'm going to do it to completeness and soundness. My upper bound on S will come through here. Okay, yeah?
It's the quadratic function, doesn't it can you just lower bound that at 1/2?
I'm not sure if 1/2 is good enough.
Because you go to 2 to k, you go to 0.
No, I understand, but I think I want a better lower bound under some assumption. I want something like 3/4. But yeah, it's a quadratic function, and yeah, that's a good observation, but I think I want a better lower bound for getting my gap. So for now, I'll just leave it like this, and now we'll just connect these statements to the completeness and soundness there. Okay? All right, so let's continue. Almost there. But the point being is like, at high level, this analysis, should make some sense in the sense that the winning probability, is bounded to the ratio of the size of the set over the ambient space, right? Or it's not so much ambient space, but number of possibilities here, right? And on the other hand, if the set is reasonably large, then you should get your probability should get better, okay? All right, so now where do I want to make some space? All right, let me just go here so we keep the graph-no isomorphism part. All right, so if S, let's start with soundness first, is less than k over 2, what can we say?
We can directly use the union bound.
We can directly use the union bound. Then probability of accept is at most S over 2 to the k, that was the union bound, which is, using this thing, less than a half size of k over 2 to the k, which is what we claimed in the soundness case over here, right? Okay. Let's say that instead, if S is at least size of k, then probability of accept is what?
Use a previously derived bound.
This one here?
Yes.
I agree. But then we need to do something, okay? So this is at least S over 2 to the k, 1 minus a half S2 to the k. Okay? But we still need to say something, right? We need to get to 3/4 k, right? And I'm trying to figure out whether my assumptions over there about S are kind of good enough or not. And maybe you guys can help me in the meantime.
Doesn't this work if we put substitute k, then on for the left S, we change that to 2 to the k minus 2?
Okay, so first, okay, maybe let's just try to blindly go for it. Okay, so we put in this one. That's clearly something I can do because S is at least that much. Okay, but here, I need an upper bound on S, right? Right. So I think this is the assumption I kind of lost somewhere, and I thought I had it in my notes. And I think I want to assume somewhere that the size of S is not too large relative to 2 to the k. Why am I getting confused?
Well, we said that k was in between 2 to the k minus 2 and 2 to the k minus 1, and then we said there's a relation between S and k, so can't we use that?
But still, the fact that k is bounded between 2 to the k, those two things doesn't tell me that S is upper bounded by something, right?
Well, it's upper bounded by 2 to the k minus 2, right? Or, sorry. Oh, sorry. Upper bounded. My bad. Yeah.
So those sandwich capital K, but what I need is an upper bound on capital S, right?
Well, if S was bigger than 2 to the k, you'd have one by trivia. You'd have a collision, right? Into this.
So yeah, maybe I want to say that kind of what I need is that this thing cannot be more than 2 to the k over 2. And the reason why I want that is, well, first, later, maybe I can just live with that, and maybe that's good enough. But yeah, let's use the assumption for now, okay? Because if I have this, then clearly, like, I'm done there, okay? So let's introduce it now, and then it's just some assumption on a set lower bound protocol, and when we tie it back to GNI, we'll see if we're fine, okay? So in this case, I can use the upper bound, which is half, right? And I get this at least 3/4 k to the k, okay? Which is what we wanted. Everything clear? Up to the assumption over there. Sorry about that. I thought, yes, I must have lost that somewhere. Okay, now we have a set lower bound protocol, and now we're going to tie it back to GNI, right? So here's where we left off at GNI, right? And we want to construct a public coin interactive proof for that one. So let's do that. So we have a prover, and we have a verifier. Their common input are two graphs, G0 and G1. If we want to use this set lower bound protocol, what should they do to begin with? What's the first thing they're saying? So first, they're going to do some sort of, each of them in their mind are going to do the same computation. They're going to set capital K to be the target size. What's the target size? 2n factorial, right? Okay. And then they're going to set S to be, that thing over there, right? So it's going to be whatever is generated by G0 and whatever is generated by G1. Now, of course, it's not like the verifier writes down S. It just thinks that S is that, right? So now we have set, those parameters. We also need to make sure that we pick things so that things there actually make sense. So let's see that we do that. So M is a sort of number of bits to represent an element in S. Okay, so for example, you could imagine that M is just a n by n, which is the adjacency matrix for one of these graphs, right? It doesn't have to be like a tight representation. It can just be any reasonable representation. Okay. Now K, little k, we said earlier that is just anything that sandwiches K like that. Okay. K sandwiches capital K. Okay. So those are sort of parameters that both of them set, right? And now they have to both run the sort of set lower bound protocol, which consists of sending H and Y, right? And getting back some graph capital H. This graph capital H is the candidate pre-image X here, right? Together with an isomorphism phi that certifies that capital H is indeed in this set S. Okay? So I'm just tying back how things look like there. And let's analyze completeness and soundness and figure out how to make that assumption hold.
I think you can get rid of the assumption by...
Okay.
So in the completeness case, right, if the set S is larger than K, then the prover can just choose a subset of S that is of size exactly K and then run the protocol. And this, then you just kind of pretend that S only has size exactly K.
Okay, and then it's bounded.
Yeah.
Okay, fine, good. All right, so it will basically refuse to do anything if it happens to find a preimage in S minus k.
Yeah, I mean, it doesn't make sense from, like, obviously the probability will only get better if you do this,
Yeah.
but from the analysis, you just pick just a subset.
Thank you very much, Nick. Did everybody understand the proposed fix? Nick, maybe you want to repeat it one more time?
Okay, so in the analysis of this probability that go over X and S, you can just look at the probability that there exists an S and X and a subset of S that has the size exactly K. Right? And this is kind of, the probability that you want is at least this, and then you do the analysis from that subset. And this gets rid of this annoying.
Good, and also maybe for an additional explanation that line is that in this particular case, we choose capital K to be exactly the correct size of S. So we don't even have to look at a subset thereof because we know what the size is and we just set it. Okay? And then for this capital K, because of the choice here, then we're good. Okay? All right. Sorry, it was like really bothering me like until I found it. Okay, good. So, okay, let's look at this protocol. What's actually happening here, right? So, can anybody give me like some high-level intuition on what the prover is trying to do compared to the private coin protocol? Clearly in isolation, what the prover is doing is solving the set lower bound protocol. But now we want to try to think about the protocol that came out of this sort of application of set lower bound protocol and the protocol that we saw in lecture 1. Okay, so while you think about it, I'll just put the original protocol here. And we'll see some analogies. Thoughts? All right, so here's some thoughts. See what happens in the completeness and soundness of this original protocol. If the two graphs are not isomorphic, that means that there are many, many possible verifier messages that the prover can answer. Okay, because it can always figure out back the answer. Right? So in particular, there are many messages from a verifier for which the prover can choose like a winning combination, a winning continuation. Okay? If the two graphs are isomorphic, this is the soundness case, then the probability that the verifier, that the prover can continue and win is smaller. In particular, it falls from 1 to 1/2. Okay? So what's happening in this protocol you can think about is basically the prover is trying to convince the verifier is that it has a high probability of winning in this protocol. Somehow there are many choices of the verifier's randomness that led to a winning prover strategy. Okay? Now, this intuition is roughly what lets you prove this inclusion. Because to prove such an inclusion, you can't go to every interactive proof and do something local there. You have to do something generic, right? Something that works for everything. So what actually is going to happen in this inclusion is you're going to go round by round in the private coin protocol. And instead of the verifier actually sending the messages, they will engage into a variety of set lower bound sub-protocols round by round. And in each round, the prover will convince the verifier that it has still a high probability of winning for the rest of this protocol. And it continues and continues like that, round after round. Okay? Again, the analogy You can already see it here, okay? Where here the prover is convincing the verifier to say, hey, look, there are many settings of your randomness, okay? There are many possible messages you could have sent me that that lead to a good outcome, okay? That can make you win. Like make me win, sorry. Okay? Questions? Okay, so some other remarks. Notice that this transformation doesn't really use algebra, which is also curious, right? Because it seems like after the first lecture, we basically left behind combinatorial techniques and started using only arithmetization. That's the only thing that gave us mileage for a few lectures. And yet, we're back here with a rather powerful thing that says, look, you can actually get rid of private coins in general, and all you really need is pairwise independent hashing, okay? Now, of course, the construction we had was using algebra, but it's not really using algebra, okay? It was just using, some properties of linear transformations, okay?
I have a question.
Yes.
So in the generic case, how to compute the certificate true for the
How to compute the certificate?
for the general?
Yeah, I mean, the generic case is more difficult. No, it's actually quite messy because you have to define correctly the set S for every round, okay? And this membership thing, I don't even remember whether there is a sub protocol for that too, or whether it comes out of other things. I don't remember exactly, but it's actually a rather remarkable proof. Already the basic case is quite. It's quite surprising. The general case is non-trivial. It's worth to look at, I think, but yeah, I don't know the answer right away. What else I wanted to say about this? By the way, that's also a good question, and yeah, you should go and look. A few years ago, there was something that you do lose in this transformation is the soundness gap. Okay, so first and foremost, you're losing perfect completeness, and also the soundness gap between. If you look at a generic transformation from an interactive proof that has some completeness and soundness, after you transform it, actually completeness and soundness kind of get closer and closer, and you have to re-amplify, okay? I will post on the website a link of very recent paper, actually, I think a couple of years ago, where somebody revisited this transformation and actually provided a more refined and sort of, to some extent, more natural way to transform private to public coins that preserves the soundness gap up to a constant. Okay, so that's actually a very nice result, and I think it's also very well written. That's, for example, one place where it might be easier to read about the entire result rather than the original paper. Another thing that's happening here is that we're losing perfect completeness, which is kind of annoying. And however, it turns out that in general, I can give you an interactive proof with imperfect completeness, and I think at the cost of maybe one round, you can recover a perfect completeness. This is something that we're not going to cover in this course. It is sort of related to techniques that show how to place BPP inside the polynomial hierarchy. Okay, they're kind of, they're not that difficult, but they take an entire lecture to kind of tackle, and this is not necessarily the focus of this course. We want to try to get to a sort of delegation of computation at some point before the semester ends, right? So if we start doing complexity theory course within this course, then we don't get to have this course. But I definitely encourage you to look at, for example, in Aurora Barak book, how do you recover perfect completeness? Okay, I think that's if you haven't seen that, that's a sort of rather sort of foundational technique in complexity theory. Again, it's related to how you place BPP in the polynomial hierarchy. Okay, so I think today I planned so less heavy lecture than last time. So I think that's all I wanted to say for now. Next week we'll look into other ways in which interactive proofs are limited, and maybe to give you a preview. One is which languages you can prove, another question you can ask, which is sort of related to the efficiency questions we'll ask later this course, is how much communication is necessary to prove a language, okay? So for example, we saw that for unsat, I can prove to you using polynomial communication, as opposed to you iterating over all witnesses, but that's fine. But let's say for sat, okay? Can I give an interactive proof where the communication complexity is less than what would have taken for me to communicate to you a satisfying assignment? Okay, that seems like, maybe. Why not? Maybe there's some magical proof that I only give you square root 10 bits and I convince you that the formula is satisfiable. Okay? So we'll see what happens with this small communication interactive proofs. And so that will be a subject of next time. Okay.